free stream far away from the wing, the velocity begins to decrease as you approach the surface of the wing. And there's this little space on the surface of the wing, about the thickness of a dime, really. It's called the boundary layer. And inside that boundary layer is where all this velocity transition occurs. Outside of that thickness of a dime layer, then the rest of the velocity is as if the wing wasn't there, the free stream velocity. So everything that we want is contained inside that boundary layer. If we can get that boundary layer to stick to the surface, we have lift. And if the boundary layer separates, we have stall and the wing falls and people get hurt. Okay? So our goal is to keep that boundary layer stuck to the surface of the wing. So I wanted to show you another little picture of what it looks like when you have separation of a boundary layer, if I can, if it lets me. Let's see. Control, click. Or not. Oh, that's not control. Okay, so what you're going to see here is a two-dimensional wing, or shape of a wing, put in bubbly fluid that's moving quickly, and you can see, let me go back. Yeah, it's completely separated. Let me go back. So here you have nice smooth flow over both the bottom and the surface, and as you increase the angle of attack, the boundary layer, that surface on the top of the wing, begins to separate from the wing, and then what we got is, after separation, you get what you call turbulence. And turbulence means you got all the pressure that you used to have, that nice low pressure, now it begins into high pressure and you lose all the lift and the suction is gone and things go bad. So that's what it looks like when you have separation of a boundary layer. And now, maybe escape, is that what you said? Oh, let's go back and close this off. And I don't know what that is. Okay, so there's that pressure distribution I was talking about. And when I told you I was going to talk about math a little bit, so I wanted to show you what the equations look like that predict this boundary layer. How do you predict how fast can you go before the boundary layer separates? How fast, or what kind of curvature you can have before the boundary separates? If you keep that boundary layer on there, how can you manipulate it on paper? How can you predict what's going to happen? So again, let's see, control and choose. Sorry this takes so long. It's so much faster when you just know the equations, you can write them up on the board. Okay, boundary layer equation. This is just from Wikipedia. And there's these two guys. One was something Navier, and the other guy was something Stokes. And they created these equations, which you can see here. And they're incredibly complicated, which you can see here. And they're incredibly complicated. So basically what it says is, well, let me see if I can't give you meaning to some of these symbols. You know, you studied in some of your classes lines that have slope, right? And a line that has slope is, another word for it is average rate of change. So when you go into pre-calculus, the word slope, the rise over run, has a new name called average rate of change. Well, there's a symbol for average rate of change. You use the symbol delta, the change in a formula that produces results. So the change in the formula divided by the change in the inputs for that formula, right? So this is called an average rate of change, where x is your input, and if you change the input, you're going to change the output. And this is the symbols we use for slope in pre-calculus. It's an average rate of change. In calculus, we take this notion of an average, and we shrink it to an instantaneous rate of change. How quickly are things changing at this moment, at this spot, at this exact spot, not average number of spots. And so this is the symbol we use for what we call a derivative. It still means slope, like this one does, but this is instantaneous, where this is average. So the symbols that you see up there are a little bit curved. Let's see, you've got U's and V's. what direction is that one? X and Y. So this symbol right here is an instantaneous rate of change. But remember that we're in 3 dimensions now. We can go horizontal, left and right, and we can go vertically. So every direction has its own little coordinate. You can go X is one way, Y is the other way in 2 dimensions, and then Z would be your 3rd direction. And when you track a particle in space, in 3-dimensional space, you have to track its 3 coordinates of wherever it is. So what this says is, in the X direction, instantaneously, right, we've got a velocity, a change in the velocity, so this is an acceleration symbol. How quickly is something changing in this direction at that moment? So these are very complicated equations where we have velocities in X direction and Y direction, we have densities, we have accelerations right here, we have viscosity, the thickness of the fluid again, and basically in order to work with these equations you have to make all kinds of assumptions to whittle them down into something that's more simple. There's no way you could go out and try to solve these equations for all of them at the same time. So we do things like, well, let's pretend we're really close to the surface. Or let's pretend that this, this number or this value is really small so we could neglect it. Let's pretend instead of being a curvy formula, let's pretend it's a straight line formula. And if you make some assumptions, then these very complicated equations break down into a very simple equation right here. I don't know if you can see it. And this is the basic equation for a boundary layer. It has to do with how fast it's moving times how fast it's moving in that direction, and the viscosity, and how quickly that fluid is accelerating, vertically at least in this equation. So we can use mathematics to predict properties of this boundary layer. And once again, all you want is this little boundary layer to stick to a surface, and you want to know when is it going to separate before you actually go out and try to fly this thing. So let me close this. And scroll down. Okay, so once you've established that you can fly, now you know that there's this boundary layer. The next thing is, what can you do with this flying wing? Well, we can carry things, we can travel, and I'm sorry to say it, but a lot of the great inventions in flight especially were because we wanted to kill people. So in order to answer these questions, we have to answer things like, well, we have to consider that things have weight. People want to feel safe and comfortable if you're going to take them up in the air. And if you kill people, you need to be fast in order to get away from people that want to kill you back. So let's talk about weight. There's this, the equation that I told you about earlier, which is F equals ma. But instead of thinking of it as acceleration, we could think of it as, well, let's see. We have a wing, and we want it to carry things. So the things that we carry, they're going to have weight. So we want the wing to be able to generate enough lift so that it can carry the weight that we put on it. So let's see. You're going to have air that moves across the surface of that wing. And as a result of the curvature, some of that air is going to be pulled downwards towards the wing or towards the ground. And so